Using second derivatives to find maximum minimum values in sketch graphs. Classify the extreme of a function using second derivative tests. Graph can function in a manner that shows concavity. Is concave up on the interval if the derivative is increasing. It's concave down on the interval if it's decreasing. If the second derivative is greater than 0, the interval is turning up, it's concave up. So it's positive there. So you have a happy smiley face. It shows a minimum. If the second derivative is negative on the interval, then it's going to be sad. So you have a maximum there. So and it's turning down. So concave down. Suppose that f is differentiable every point on the interval, then there's a critical value c for which f prime of c is equal to 0. It's a minimum if the second derivative is positive, and if the second derivative is negative, then you have a maximum there, because it's sad. So so we see what happens when it's greater than 0, when the second derivative is less than 0. But when it's equal to 0, the second derivative test fails, and we have to use the first derivative test. Here they ask us to find graph the function by relative extrema. So I find f prime and f first and second derivative. Then I set that first derivative equal to 0. So you have critical points at -3 and 1. So I check the behavior of the second derivative using those critical points. So f of -3 is less than 0 of a negative. So I have a maximum there. And f of 1 is positive. So I have a minimum there. So the point location is found at 3, -14. That's a maximum. And -118 is a minimum. And that's what the graph looks like here. And there's the graph there. So with those, you know the max and the min, you know how it's going to curve. So here's this graph function by, and then find the extrema. And there's that right there. There's the graph there, and you see the graph of it here. So the first thing I do is I find my first and second derivative. Then I set my first derivative equal to 0. I know that e to the x will never be equal to 0, so I'll go ahead and solve 2e to the minus 1 equal to 0, and I say equal to 0 and solve for x. Taking a log of both sides, there's my critical point. Then I check the behavior of that critical point on the second derivative. I check the behavior of it, and I see that I have a number that's greater than 0, so it's positive, and that means I have a minimum there. I found the y-coordinate for that location, so I know I have a minimum at that point there, at that location. Okay. Okay, for this one here, find the extrema given by this point here. First thing I do is I find this first and second derivative. Then I set that second derivative equal to 0 and solve for x. So in this case, I have 3 critical points. Okay. Therefore, next I check and analyze the behavior of those critical points on the second derivative. And I put a 0 in here, I get a 0. The second derivative test fails, so we end up using the first derivative test at around the critical point of 0. So I pick -1 and -1/2 and +1/2. I'm using the first derivative test now. In this case here, for both of them, it's greater than 0. There's no extrema, no change. Okay, so now I check it at, use the second derivative test for 1, and it's negative. So I have a maximum there. Then I use the first, then I use -1 on it, and I end up with a number that's positive. I have a minimum there. Okay. So I have a max and a min. A max at 1, 4, and a min at -1, -4. Points of inflection with the second derivative is 0, or it doesn't exist. So given a point here, they want us to find points of inflection. So find where it's g prime is 0, it doesn't exist. So I set the second derivative equal to 0 and when I solve for x. So I'll get a 0 at when x is 0, and I have a 0 at minus square root of 2 or positive square root of 2 over 2. Those are my 2 points of inflection. And here's another example here. Find what g prime is 0, so I set it equal to 0 and solve for. Okay, now I take the natural log of both sides, and there's the x coordinate for my point of inflection. The y coordinate is at -316. So my point of inflection is at that ordered pair there. This point of inflection is where the concavity changes. Now this one here asks us to find the relative extrema for the function. So I find my f first and second derivative, and I set my first derivative equal to 0 and find the critical points for it. And the critical points are plus or minus 1. And they go ahead and they found the y values there, the y coordinates for them. So next thing I do is analyze the behavior of the second derivative using those critical points that I've already have. So critical points are -1 and 1. One is if a -1 is negative, so I have a maximum. F of Positive 1 is positive, so I have a minimum. Concave up. And there are the locations of where the minimum and the maximum are. Okay. Then they ask us to find the inflection points. So I'll take my second derivative set equal to 0. X is 0. So I'll find the y coordinate for that location. It's 2. So I have an inflection point at 0, 2. And there's the graph of it there. And there's the graph of it there. This one here asks us to find max and min, sketch the graph. So the first thing I do, I find my second derivative. Okay, yeah, it exists everywhere. Next thing you know, I find what the first derivative is 0. Okay. So 1 0 is going to come from when I factor it. 1 0 will be at 0. The other ones will be at where 4 minus x squared is. So I'll take that and set equal to 0. So I have a 0 at 0, 2, and negative 2. So the next thing I do is analyze the behavior of the second derivative using the critical points I had found. Okay. So f second derivative at 0 is positive, so I have a minimum there. Now I add the point 0, 1. When I put in a positive 2 here, it's less than 0. It's negative, so it's sad. I have a maximum. Next one I put in f of negative 2. Gives me a number less than 0. So that's negative. I have a maximum there. Let's concave down. So positive, negative, negative. So 217 is a where's that? 0, 1 here is a minimum. 217 is a maximum. It's in a relative maximum. It's increasing there. Okay. Now it asks for inflection points, so you end up setting it equal to 0 and solving for x. Take the second derivative and set it equal to 0 and solve for x. And that gives me my points of inflection. So it's concave up on. It's concave down on the intervals negative infinity to 2 and 2 to the positive infinity. It's concave up on the interval negative 2 to 2. And those points come from using the inflection points, are the points that set dividers between concave up and concave down. Once you found it. Alright, for this one here, graph the function. List the coordinates of any extreme points of inflection. State whether the function is increasing or decreasing, where it's concave up and concave down. So found the first and second derivative. I do that here. I found my first and second derivative. Okay, so this function will never be equal to 0. So I look at where it doesn't exist. It won't exist when 2x minus 5 is equal to 0. For some value. So I plug in, and I solve for. So 2x is equal to 5 halves. That's the only critical value we have. That's the only critical value we have here. So the coordinates of that location when 5 halves and 1. Oh, okay. So we plug in here, we found our critical value at 5 halves. So once that part is done, analyze the behavior of it using the second derivative. So the second derivative here at 5 halves, it's undefined. So use the first derivative test to see what's going on around those points of 2.5. So it's positive on both ends, so it's not an extreme. Find when the second derivative is 0. Find the critical points, meaning inflection points here. Okay. Inflection point at 5 halves 1. So we found our points of inflection here. It changes sign. So 5 halves and 1 is our point of inflection. And there's our point of inflection, and there's our graph, and there's our summary.